Hello viewers, welcome you all. In this video, I am going to explain the working of a ceiling fan. Many of my students have asked me that how a ceiling fan work. What are the different parts of a ceiling fan? What is the role of a capacitor in a ceiling fan? To explain all these questions, I have made this video. In this video, first of all, I will explain the theoretical aspect of the ceiling fan. Then I will demonstrate practically the different components of the ceiling fan. I will deassemble a ceiling fan and I will show all the components, and I will explain the working of the ceiling fan. Let's start, right? So we'll take it down from the ceiling, and we will remove the blades, right, from the fan. Then we will remove this cup. Now we can see here there is a capacitor connected here, right? And these are the different nuts, 1, 2, 3. You can see here, and these two are for connecting blades. So now I am opening these 3 nuts. So you can see here, when I opened this casing of the fan, I found inside the fan these 2 coils. You can say one is outside and one is inside. There is a rotor here, right? Now this ceiling fan contain 2 important things. One is a rotor, this one, right? And this is one is a binding of the fan. This winding is on a core. I will show you, right? When we'll take it out, you can see now this is the core, soft iron core, obviously it is, and this is the rotor that I was talking about. This part is called rotor and this is called stator. This is connected with this shaft, right, of the fan, that is connecting that is used for connecting the fan with the ceiling at the top, right? Now these 2 windings, this outside winding is called a running winding, whereas the winding inside is called a starting winding. Now we will see what is the reason for selecting these 2 windings in the fan. As far as this core is concerned, you can see here that it is made up of small pieces. After joining them together, this is made of soft iron, and it is insulated by making the use of varnish and lamination. All these things are done to reduce the various losses taking place inside the core, like eddy current loss, hysteresis loss, etc. Right? I'm going further. You can see here. Now this is rotor. As I told you, again it is made up of, and this rotor is connected with the casing of the fan. That actually this rotor is rotating along with this body of the fan, right? This stator is not going to rotate. It is connected with the shaft, it is connected with the ceiling, right, for hanging. So this is stationary. Only this part, and this part is rotating because of this rotor, right? You can see here. Now I removed all the parts. I removed the shaft. This is starting winding. This is the running winding, right? We can take them out. Now you can see here we have even used plastic strips inside these all holes for connecting the different turns of the insulated copper wire. This is done to provide a proper insulation inside the binding. Right? Now you can see, I told you that this core is made up of after joining different pieces together, which are laminated, and it is done in order to prevent the eddy current loss and hysteresis loss, right? Now you can go further. Now we know very well this is the coil that suppose we have initially one coil. You can see here, when it is connected with the alternating current AC, alternating poles will be formed, north south, right? And these poles will get inverted after every cycle. In AC we have alternate cycles, positive half cycle, negative half cycle. Polarity is changing continuously. it is changing 100 times a second, because in India we are using 50 hertz frequency for the AC. So it means these poles are changing. You can see, right? North, south, right? So they are continuously changing, right? So in this way, we are not getting a rotating magnetic field, right? Or we can say we are not getting the effect of rotation. If I place now this rotor that is made up of soft iron outside this winding, right, then what will be the effect? This conductor is placed in the changing magnetic field, so eddy currents will be set up in this rotor, and when the current flow in this rotor, now this current carrying conductor is placed in a changing magnetic field. So a torque will be developed on this rotor, right? Because when we place a current carrying conductor in magnetic field, it experiences a force as well as a torque, right? But here when we are using single coil, right, we are not getting resultant torque because the poles are changing alternatingly. You can see here, right? So there is no resultant torque here on the rotor, right? Because in every cycle we are getting the change in polarity, right? So this single induction motor is not going to self start, but if otherwise, if I start it with the push or pull, then after it can move. But it is impossible for this motor to get a self start because it don't have a self starting torque, right? Now to remove this problem, what we will do, we will take another coil here. You can see here, right, how the poles are changing with the change in polarity of the AC, right? So we are not getting rotating. You can see here AC is changing with the time, right? So the one cycle, the torque is in this side, and for the other it is in this side. So the resultant torque is 0, we can say. You can see from here. Now what we will do? We will, put another coil inside this outside coil. That will be called static winding, and this is called running winding. Now here one thing is very important. We have seen that there was a capacitor, right? Now these two coils, this starting as well as running, two ends of them are joined together here, and they are connected with the neutral of the AC. Whereas the other two ends, this end is directly connected with the phase for the running winding, but for the starting winding, we are using a capacitor. So when we are using a capacitor, means the current in this starting winding will be leading by a phase angle of pi by 2. It means the magnetic flux, magnetic field arising in this coil will be leading by an angle of pi by 2, right? So we can see it further in this animation. So now I am going to put a coil here inside. You can see here, this is for running winding graph and this is for starting winding. You can see in the starting winding, the electric current is leading by an angle of pi by 2. And this is the diagram for, rotation of the magnetic field. You can see here, this blue arrow is for the current in the starting winding, right? Red arrow will be, you will see red arrow here, that will be for the running winding, right? You can see here, and this is the resultant magnetic field, right? You can see here, this was the resultant magnetic field, this pink, right? Blue was a starting winding current, and we can represent here, starting winding magnetic field, blue, and the red is running winding magnetic field. You can see here. So you will see how this magnetic field, resultant magnetic field, will rotate with the passage of time, right? You can see at the different angles, right? So you can see here at 90 degree, at 0 degree, at 45 degree, right? We are taking the corresponding angles from here, right? So you can see with the passage of time, right, the resultant magnetic field is rotating, right? So this resultant rotating magnetic field is producing a rotational effect. This can be, used, formula can be used for calculating the number of rotations, right? So you can see here, now when I have two coils, right, this is the inside coil, that is, we are saying starting winding, and the outside is a running winding. So when and capacitor is connected there, so you can see now we have a rotating magnetic field, right? Right. So when I place a rotor outside that magnetic field, it will experience a torque and it will start rotating, and the fan will start rotating along with it, right? So this is all about it. Now I will show you the practical demonstration of this.